Quality control is a process of making sure the software we are producing works as advertised. We would like to have some measure of quality of the software we are building. Typically, this is done by exercising the software to a certain inputs and comparing the outputs against expected outputs. Discrepancies between the expected output and the actual output are identified as defects. And defects can then be resolved in various ways, such as actually fixing the software, workarounds, doing something manually instead, or just accepting them. Quality assurance is a process of removing defects before delivering a software product as complete. This is in contrast to the common use of the term QA or quality assurance. As software engineers, we practice quality assurance through the application of several techniques such as code reviews and design reviews, requirements reviews, inspections, audits, pair programming, or formal proofs of correctness. A product defect is a discrepancy between a desired behavior of a software product and its actual behavior. In contrast, a requirements defect is a problem with the requirements themselves from where developers derive the implementation. Requirements defects can be due to incorrect or incomplete or missing or conflicting requirements. As engineers, we are mostly aware of defects deriving from incorrect implementation of some feature. As developers, we strive to improve the quality of the software we produce by implementing several organization strategies. We do code reviews, we merge each other's code, we do pair programming, etc. Now, many studies have shown that the majority of bugs or product defects developers end up fixing actually can be traced back to requirements defects. Quality assurance needs to begin at the beginning. That is, when we are defining or agreeing on the software we intend to build. In other words, QA needs to begin when we are writing the requirements. Requirements need to be written with tests in mind for an objective method of testing whether we have reached and accomplished that requirement. In other words, a good requirement is that which there is an unambiguous way to measure that we have actually achieved the requirement. So we need two things. First, we need to verify to make sure that the requirement accurately reflects the agreed functionality and that they meet the client's needs. And second, once we implement a solution to the requirement, we need to validate the solution, that it accurately implements the requirement. Let's take a look at various strategies in which we can implement quality assurance. There are several strategies we can apply at different levels of granularity. At the smallest level of granularity, we can have a single line of code, a block of code, a function, or even a class. We refer to this level of granularity as the component and apply component testing strategies. When we consider several components as a collection that interact with one another, we apply a different set of strategies generally referred to as the integration testing strategies. At an even higher level of granularity, we can consider the interaction of various layers of the application dealing with various levels of concerns, for instance, user interfaces, web services, data storage, and refer to these as system-level testing. Once we've gained an acceptable level of confidence of the quality of the software, we might ask end users or proxies to actually use the product to validate the software through acceptance testing. As we address new requirements or fix defects, we want to make sure we don't introduce new defects. Regression testing is a strategy to validate that what was already working correctly is still working correctly after some significant improvement or fix has been introduced to the product. There are many strategies, approaches, techniques that deal with quality assurance, and this diagram tries to capture the extended family of all testing approaches. As mentioned earlier, there are different strategies at different levels of granularity. At the smallest level of granularity, we have components, that is, lines of code, functions, classes, etc. Tests at this level of granularity are referred to as unit tests. Unit tests seek to isolate the component under test so that it can be tested independently of any external dependency. Typically, source code is written intentionally modular to promote its testability as a single, self-contained unit. Tools such as JUnit allow creating unit tests easily. When we consider several components as a collection that interacts with one another, we apply a different set of strategies generally referred to as integration strategies. A collection of components can form a module or collectively implement the functionality of a screen. Components integrate with one another through application programming interfaces that promote modularization. Integration testing is applicable to testing web services that integrate through the HTTP protocol. At an even higher level of granularity, we find the user interacting with the application and exercising the various layers of the application. This exercises various levels of concern, for instance, user interface, web services, data storage, and refer to these as system-level testing. Users interacting with the application hosted in an environment that closely mimic the real environment. The actual behavior of the system is compared against the expected behavior. Once we've gained an acceptable level of confidence of the quality of the software, we might ask end users or practice to actually use the product to validate the software through acceptance testing. Alpha testing is done within the development team, whereas beta testing is done with actual users. As we address new requirements or fix defects, we want to make sure we don't introduce new defects. Regression testing is a strategy to validate that what was already working correctly is still working correctly after some significant improvement or fix has been introduced to the product.